Concept example number 4. So Cindy decides to go to a cow racing competition with Jim. We're given the position versus time graphs for the 4 cows. We're going to rank the cows from fastest to slowest. So we know that speed and position are related, as the velocity, or the speed, is a change in the position over the change in time. In this case, all the cows are moving in one direction. So because they're moving in one direction, the positive direction, the speed and the velocity here in this situation would technically be the same. To get the speed or the velocity from a position versus time graph, we take the slope of that line. So the steepest slope would relate to the fastest speed or the fastest velocity. So we're looking for the steepest slope. We can see here that LC has the steepest slope, so LC would be the fastest cow. Our second steepest slope, we can kind of see Betsy is going to cover more ground in a smaller amount of time. So, or our second steepest slope here would be the slope of Betsy's position versus time graph. So Betsy would be our second fastest cow. Dolly is going to cover more ground in the same amount of time that Melinda covers ground. So that means that Dolly is going to be the third fastest speed, the third steepest slope, and Melinda is going to be last. So she is our slowest cow. So slope of the position versus time graph represents the velocity. The steeper the slope, the faster the speed. In concept example number 5, we have Harry and Jim decide to go kayaking together during their Thanksgiving break. So we have the position versus time graph of both Harry and Jim transposed on the same graph. We can determine where they're in the same place by where the position versus time graphs overlap. So here we see that exactly 1 hour, Harry and Jim are going to be located in the same place. How much time does Harry spend on the river before he passes Jim? Technically, Harry is going to be on our river for, let's see, he at time equals 0, he's at position 0. Okay, at time equals 1 hour, he's at 6 meters. So that means before Harry passes Jim, he's going to spend 1 hour on the river. Okay, because a change in time before Harry passes Jim is 1 hour. The time in which it would take Jim to meet Harry would be 0.25 minus 1, we get 0.75. Okay, so Jim would pass or meet Harry at 0.75 hours. Harry will be on the river for 1 hour before he passes or meets Jim. So we look at the difference in time versus where the objects are going to meet on the position versus time graph. Last part, C, where on the river does it appear that there might be a swift current? Okay, so the swifter the current, the faster the speed. So we're looking for the portion of the graph where there is a steep slope. And that's going to occur, right? The steepest slope is going to occur somewhere between 1 second and 1.5 seconds. Okay, so I would say that time interval is between 1 and 1.25 if we were to estimate based on this scale here. So between 1 to 1.25 seconds, or from 6 to 8 meters is where the current's going to get really swift, meaning the slope is steepest. Okay, concept example number 13. So in 13, Jim is training for a race. He liked his first cross-country race, so he's training for a second race. And he's going to use a app to track his run. So he's using Strava here. How fast did Jim run during each interval? So if we want to figure out his speed or velocity during a time interval, we need to take the slope during that interval. Okay, using the slope by intercept equation. If we want the average velocity, that's asking us for the velocity for the entire trip. So we're going to take the average velocity in the origin versus the final position. So I'm going to annotate on here and kind of show you the difference. Okay. So in segment 1, we start at a position of 0, time 0, and we reach a nope. Why isn't this working? Get rid of that. There we go. Okay. So we reach a position of 20 meters at t equals 4 seconds. So to find the slope, we're going to take y2 minus y1. y2 is going to be 20 meters minus the initial y coordinate there is 0 over x2. x2 is going to be 4 seconds. x1 is going to be 0 seconds. So our slope there is going to be 5 meters per second for segment 1. For segment 2, the slope in these 2 points, okay, there is no rise, so our slope is going to be 0. Slope here is the velocity, so that means that the velocity is going to be 0 for segment 2. For segment 3, our y-coordinate ends at 40 meters, so our y2 coordinate is going to be 40. The object starts at a position of 20 meters, so the y1 coordinate is going to be 20. Our change in time, my video is unfortunately blocking the graph, but my change in time here, the initial time that it reaches a position of 20 is 10 seconds, and then the entire path of motion is going to take 17 seconds. So we're going to take 17 minus 10. Let me double check that. Let's see if I can get rid of my image here. Can I get rid of this? Okay, so our graph actually ends at 13 seconds, not 17. My video is blocking the graph there. So our time interval, or our x2 coordinate is going to be 13 seconds, and our x1 coordinate is going to be 10 seconds. So we calculate the slope there, we'll get 6.67. And our units are meters per second. So now we've calculated the speed for all 3 segments. So we move at 5 meters per second, then a velocity of 0, and then a speed of 6.67 meters per second. So that is the speed. When we see the word fast, we think of speed. That's a speed for those 3 time intervals. To find the average velocity, we're looking at the entire path of motion. So we're going to have to take a look at the average velocity equation. So the average velocity is going to be the change in the object's position, delta x, over delta t, the change in time. So we need to figure out what our final position is. Our final position, x final, is where we stop recording on our graph. So the final position is going to be 40 meters. And our initial position we can tell and assume from this graph that it's 0, 0, right? We begin at the origin where the position is 0. So I'm going to take 40 minus 0 meters. and divide by my change in time. I start at a time interval of 0, and we end at the time interval of 13 seconds. So delta t is going to be 13 minus 0 seconds. We plug that into our calculator. We get 3.08 meters per second. Okay, so our average velocity for the entire segment, we're focused on just the initial and the final position change over the change in time, versus if we're asked to find the speed of each individual segment, we need to take the slope of the individual segments to determine the speed during those segments. So our average velocity for the whole trip is 3.08 meters per second. Let's give one more a try. So in example 14, Jim continues his workout, so he's going to keep on running for segment 4, 5, 6, and 7. We want the average velocity for each of the segments. Okay, so if we're looking for the individual segment, if we want velocity or speed for the individual segment, we need to take the slope of those segments. So I'm going to have you guys pause the video and go ahead and take the slope for segments 4, 5, 6, and 7. Unpause the video once you find the slopes of those 4 segments. Yikes. Okay, so for segment 4, we should have gotten 1.25 meters per second. For segment 5, the slope of that segment from 4 to 8 seconds is going to be 0 meters per second. When we take the slope from 8 until 12 seconds, the 17 is misplaced here. So from 8 to 12 seconds, we're going to get a negative slope. That slope's going to be 8.75 meters per second, negative. Slope for segment 7, we're going to get 0 meters per second. Okay, so if we're asked for the speed or velocity of an individual segment, we take the slope of that line. If we're looking for the average velocity for the entire path of motion, so let's say that this question instead asked for the average velocity for the entire path of motion, or from segments 4 to 7, we would have to then use the average velocity equation instead. So we're going to go ahead and do that just to drive this point home. But let's say we have average velocity is change in position over change in time. Our final position is technically negative 30. So x final is negative 30 meters. And our initial position was technically 0. So our displacement is the difference between those two. So it's technically going to be negative 30 meters minus 0. We'll divide by the change in time interval. It takes, the 17 should actually be over here. It takes 17 seconds to get to that negative 30 meter mark, so we divide by 17 seconds. And the average velocity for the entire trip, we got negative 1.76 meters per second. Okay, so the slopes of the line are the speed or the average velocity for that segment. If we want the average velocity for the entire path, we need to look at the total displacement over the total time. Great, so we've analyzed how to find speed and rank speed from position versus time graphs. Let's talk about how from descriptions we can come up with what the position versus time graph should look like. Okay, so this is converting words to graphs, descriptions of motion to graphs. So for the next two examples, 15 and 16, they're based off of bedtime stories that Jim's mother has told him. And we're going to